Open up a standard desktop computer and dive past the cooling fans, and you'll find a small metallic square. This is the central processing unit. Beneath that dull metal cover lies a dense labyrinth of electrical pathways. A single modern chip contains up to 90 billion interconnected transistors, constantly firing to process your data. This chart illustrates the true scale of that architecture. We have a human hair, a microscopic dust particle, and a single FinFET transistor, the tiny switches that make up those billions of connections. Each one measures exactly 36 by 6 by 52 nanometers. Because the architecture is so small, if any chemical mixture, temperature, or measurement is off by a single %, the entire chip is ruined. Fabricating these structures is the most precise engineering challenge in human history. To build something the size of a virus, you need infrastructure the size of a neighborhood. A modern semiconductor fabrication plant spans the area of 8 American football fields. Inside, you won't find exposed conveyor belts or dirt. You find miles of pristine cleanroom floors, bathed in specialized lighting, lined with endless rows of highly automated manufacturing tools. Some of these individual machines are the size of a city bus and completely dwarf the human technicians running them. A single unit can cost upwards of $170 million. You have massive, building-sized infrastructure meticulously controlling individual atoms. To understand how a microchip is made, you must look at both the massive logistics of the factory and the microscopic physics happening inside it. Every single microchip begins as a raw, jagged piece of quartzite rock. That rock is refined and grown into a highly purified monocrystalline silicon ingot, a heavy, solid cylinder. This cylinder is then sliced into perfectly smooth circular wafers, each less than a millimeter thick. Inside the factory, these delicate wafers are stacked in sealed plastic pods called FOUPs. Automated robotic carriers grip these pods, gliding along the sealing tracks to ferry them safely between machines without exposing them to dust. Think of this blank 300mm silicon wafer as an empty canvas. It is about to enter a relentless, automated cycle of extreme atomic engineering. This animated cross-section shows the first step in the cycle, deposition. A layer of insulating silicon dioxide is laid down across the wafer, followed immediately by a layer of a light-sensitive chemical called photoresist. Next comes photolithography. Complex optics project a pattern of UV light through a stencil, shrinking the design down by a factor of 4. Where the light strikes the wafer, it weakens the chemical structure of the photoresist. During the etching phase, chemical developers wash away that weakened photoresist. Then, a highly energetic plasma burns away the exposed silicon dioxide directly underneath, creating deep vertical trenches. Those trenches are then flooded with conductive copper. Finally, abrasive pads grind the entire top surface completely flat, leaving a flush network of copper wiring ready for the next layer to be applied. By repeating this exact loop of optical projection and chemical erosion, manufacturers build billions of specific nanoscopic structures simultaneously across the entire surface of the wafer. That process creates the metallic wiring. To build the actual transistors at the very bottom level, the factory relies on a completely different tool called an ion implanter. Instead of layering materials on top, the ion implanter physically fires isolated atoms, like phosphor or boron, deep into the silicon lattice. It is a violent process that forces these new elements into the physical structure to alter how the silicon conducts electricity. Creating a complete chip requires the wafer to travel back and forth between these massive machines, repeating these microscopic operations an astonishing 940 times. By the time an integrated circuit reaches its final form, it features 80 separate vertical layers stacked on top of each other. The physical journey to build those layers takes 3 continuous months of manufacturing. Over those 3 months, the value of the material drastically changes. An empty silicon wafer costs about $100. Once it's populated with a dense grid of finished chips, it's worth nearly $100,000. With that much value on the line, the chips must be heavily inspected. Engineers use metrology tools, specifically scanning electron microscopes with nanometer-level resolution, to hunt for stray microscopic dust particles or slight patterning errors that may have occurred during the 940 steps. If a stray particle damages a section of a chip, manufacturers don't necessarily scrap the whole die. Instead, chips are tested and categorized based on how many functional sections survived, a process called binning. A chip with a defective core is simply sold as a lower-tier processor. Even with billion-dollar tools, highly purified materials, and immaculate cleanrooms, guaranteeing absolute physical perfection at the atomic scale remains impossible. To separate the working chips from the rest of the wafer, highly precise lasers slice cleanly down the grid lines, freeing the individual silicon dies. Each fragile die is then mounted onto a small printed circuit board, and a thick, thermally conductive metal heat spreader is placed over the top to protect it. This final package bridges the gap between the two worlds. It takes those 90 billion microscopic transistors and provides the robust physical connections needed to plug directly into the large-scale motherboard of your desktop. Every unremarkable household device we use is actually a direct artifact of humanity's most complex and painstakingly precise manufacturing achievement.